slides, and we've gotten into a mode where we introduce the co-host starting at 5:55. So let me share screen. Thanks again for joining us. This is the highlight of my week. All right, so I'm going to go into present mode and give it another 30 seconds. But yeah, if you're just joining us now, we've been talking about the weather and dogs and all kinds of things. And I'm sure Echo will make her cameo appearance at any moment. She always comes in to see what we're doing when it's Husky Bites evening. So I guess I'll go ahead and get started. So welcome everybody. Thank you for joining us once again for Husky Bites. What is Husky Bites? It is a free webinar hosted by the College of Engineering at Michigan Technological University, which is located in the Upper Peninsula of Michigan, and which is where we all work and play and recreate and of course study and learn. My name is Janet Callahan. I'm the Dean of the College of Engineering, and I welcome and thank you for joining us. This evening's talk is actually sponsored by Darwin and Margarita Moon. Thank you both. It's nice to have a sponsorship. If anyone listening would like to sponsor, 100% of the proceeds go to student scholarships. So I wanted to show you, we were just talking about walking and here and there, and this was up where I was just describing, Greg, where you park along the road. And what did you call that place?
Astudita. In Turning Rapids, yeah.
Yeah, Turning Rapids. And so we took a hike. The one on the right is up on one of the trails there, and so is the stump. And then the picture of the sunrise is where I park my car, which is at the bottom of the M&M building. And then I take the elevator kind of up to the 7th floor. So it's still quite beautiful here. We did have our first snow, but it didn't stick, as you can see, and it's been relatively mild so far, which I'm grateful for. So this has been our kind of menu or our syllabus for the semester. I'll be introducing Greg Odegaard and co-host William Predebon in just a moment. We have two more that follow this, with the last one occurring the Monday of Thanksgiving week, and that will be our last one for the season. And thank you everyone for joining us. This is what we will be talking about next week, which is circling around the topic of next car. And this is electrical engineering and mechanical engineering faculty member Bo Chen, who will be speaking with co-host Joe Onken, who is graduated last year with his PhD in MEME. So MEME stands for Mechanical Engineering Mechanics. MEME was a word long before there was the meme word, the M-E-M-E. So I would say meme, our meme came before that meme. So you'll hear us, when you hear us saying meme, that's what we're talking about. I do want to point out that you can ask questions as we go along. In order to do that, you just use the Q&A feature of the Zoom. So you just kind of scroll down, you ask in the Q&A. If you are watching it through Facebook live stream, of course, you can't do it like that, but you can ask us a question by sending us an email. All right, so I'm going to stop share. Thank you again, everyone, for joining us. And at this point, what I would like to do is introduce my co-host this evening, which is Dr. William Predebon, and who I will be referring to as Bill or Dr. Predebon. Dr. Predebon, first of all, is the chair of MEME, which I've already described, and he's not only the chair, he has been the chair for 25 years. This is his 25th year of being the chair, which is the head of the department, sort of the leader, and it is his 46th year at Michigan Tech. Did I get that right, Bill?
Absolutely.
All right, finally. Bill was born in New Jersey, in Trenton. He then, I guess he was told by the Catholic nuns that he had to go to earn his degree at Notre Dame. Did I get that right? It's more or less.
Priest, yeah.
Where he earned his Bachelor of Science, and where we were talking earlier about when he was a junior, he began to box and actually won the championship that year, which is an interesting story. He then went on to straight to grad school to earn his master's and PhD both at Iowa State, which is where he learned to love teaching and where he found he was actually very good at doing so. So then he was 6 months full-time Army Reserves, Army Reserves training, and then he served in the Army Reserves for a while. He worked for about 5 years at the Army Research Lab, where he was blowing things up, which was part of the experience that he learned, modeling, kind of what happens in when you blow things up. So after that, he joined us at Michigan Tech, where he has served the rest of his career, really advancing the Department of Mechanical Engineering, Engineering Mechanics, and where I met him 4 years ago when I joined Michigan Tech as the Dean of the College of Engineering. All right, so with that long intro, Bill, I'm gonna leave it to you to go ahead and introduce our key speaker this evening, Greg Odegaard.
Yes, it is my honor and pleasure to introduce Professor Greg Odegaard. Professor Odegaard is the John O. Hallquist Endowed Chair in Computational Mechanics in the Department of Mechanical Engineering, Engineering Mechanics at Michigan Tech. He is the director of a $15 million National Aeronautics and Space Administration, known as NASA, National Institute for Ultra Strong Composites by Computational Design. So what is that? Well, that is focused on the development of the next generation of composite materials for manned deep space missions, such as Mars. What is amazing, it includes 22 faculty from 10 of the top universities in the nation, 2 companies, and the Air Force Research Lab. He was a Fulbright Research Scholar at the University of Science and Technology in Trondheim, Norway in 2013. Before joining the faculty at Michigan Tech, Greg was a researcher at NASA Langley Research Center from 2000 to 2004. He received his PhD at the University of Denver in 2000. His research is focused on computational modeling of advanced material systems, which is from the quantum level to the continuum level. So that's from the quantum level to where we can physically touch things. And has over 200 journal and conference papers published. An important indicator of the value and contribution of a person's research is how often your research is cited. His research has been cited over 8,800 times, which is phenomenal. He's a fellow of the American Society of Mechanical Engineers and associate fellow of the American Institute of Aeronautics and Astronautics, and has won several awards for his teaching and research. Greg is one of those rare faculty who excels in everything he tackles. His hobbies include running, mountain biking, coaching his kids' soccer team, cross country and downhill skiing, and a variety of others. A fun fact is that his uncle and cousin are the founders of the JanSport backpack company. Thank you.
Okay, thank you very much, Bill. Yeah, I'll expand on that a little bit. So many of you probably have a JanSport backpack, or you get on the elevator here, on campus, you see students with JanSport backpacks all the time. So yeah, my uncle and first cousin, once removed, are the founders of that company. My mother was one of the very first employees of that company as well. And of course, it's exploded now, and you see JanSport everywhere. So at home, I have all kinds of old JanSport tents and sleeping bags and backpacks. So it's all quite interesting how it evolved over the years. Thank you.
Sounds like your family was outdoors people.
Yeah, they are. Yeah.
Yeah. No, that's good.
Yep. Well, thank you very much, Bill. I guess what I'll go ahead and do is share my screen so I can go ahead and start this presentation. Okay, I think you can see it, correct?
Yes.
Okay. Well, thank you everybody for joining us this evening. It's my pleasure to be here. This is a really neat forum. I really enjoy it. So today I'm going to talk about what Bill had already alluded to. That is USComp, and I'll repeat what that acronym is here in a little bit. But really, it's all about the next generation of composite materials for crewed deep space missions. We used to say manned deep space missions, but then NASA asked me to start saying crewed deep spaces. So it's not crewed as in C-R-U-D-E, but C-R-E-W-E-D. All right, so our first poll question for the night, we're gonna have 3 of them, and we'll start off with one right away. This question is, I'll read it and then I'll explain it a little bit, and you can start thinking about how you're gonna answer it. So the question is, how much does the fuel cost to send a human plus cargo to Mars? All right, so if you're sending a human or multiple humans, and you have all the cargo like water and food to go with them, how much does the fuel cost, the rocket fuel cost, to send every pound of cargo to Mars? So we'll wait, I guess we'll wait.
And you've got order of magnitude choices here. So $1,000 per pound of cargo, $100,000 per pound of cargo, $1 million per pound of cargo, and then $1 billion. And people are going for B or C.
Yeah. Always go, if you don't know, always go for B and C, right? That's always a standard rule. So it looks like we're up to what, 125 votes?
Yep. It looks like B's got it. You think is that right?
So let's see. So the people have spoken. The people think the answer is $100,000 per pound of cargo. I'm sure I saw some of my graduate students are here. They did not answer B. They probably correctly answered C, $1 million per pound of cargo. In other words, if you're going to send a human to Mars, then let's say it's me going to Mars, and that's, I weigh about 160 pounds. Think of all that, just to transport my body to Mars by itself is $160 million in fuel currently with current state-of-the-art technology. So it's a pretty scary number, right? Okay. Well, so yes, so the correct answer is in fact C, $1 million per pound of cargo. So let's talk about that a little bit. Let's talk a little bit about, oops, going the wrong way here. Let's talk about composites. Now, many of you may be familiar with composites. That's most of the aircraft you fly on now, most of the modern aircraft are mostly made out of composite materials. You see them in high-performance sports cars. You see them in mountain bikes, tennis rackets, golf clubs. If you buy golf clubs and they call them carbon golf clubs, what that really means, it's carbon fiber composite golf clubs. And these are materials, you can kind of see a picture of it there on the left. These are very lightweight materials. Like if a good portion of a lot of Corvettes, for example, or other high-performance sports cars are made out of this because it's a lot lighter than aluminum. It's lighter than steel. And if it's lighter, it means it goes faster, right? If it's your tennis racket, if it's lighter, that means you can swing it harder. If it's lighter, that means your golf club is lighter and can swing more powerfully, right? All these things go into factor. And in fact, if you're on a Boeing 787 or a Boeing 777, you're on an aircraft that's made of a lot of this carbon material, and it's lightweight. And as the name implies, it is mostly made out of carbon. Now, of course, our technology has gone a long ways with carbon fiber. We can now build airplanes out of it. Like I said, most of you have flown on airplanes that probably are mostly made out of carbon fiber. The issue there is, as we see on the screen right here, is that current state-of-the-art carbon fiber composites simply are not strong enough for manned deep missions to space. What does this mean? Well, think of it this way. We can routinely send a robot to Mars, right? We send rovers to Mars. We had one not too long ago. We've done, and we're not the only country to do that, right? So sending our little robot to Mars is really not, it's a technical challenge, but it's something we can overcome. But, robots are not very selfish creatures, right? Humans are very selfish. Humans, apparently, they need a lot of water, they need food, they need space, they need air, they need to bring their teddy bear with them. They need all this stuff that weighs a lot. And you put it all into a rocket, and all of a sudden this rocket gets really heavy, and it has to be a big rocket. So if you put all this stuff in the rocket, it's got to be a big rocket. If it's a big rocket, that means it's going to need more fuel, right? If it's going to need more fuel, that means it's going to weigh more because of the fuel, which means you need more fuel to overcome the weight of the fuel. And before you know it, sending a human, at least one human to Mars, really becomes a huge technical challenge beyond sending a rover. And as it turns out, NASA did some calculations, what you saw on the previous slide, and that is because of that, because of all this mass with water and food, then that's where you come up with $1 million per pound of cargo number. So NASA also did some calculations, probably about 5, 6, 7 years ago, that said that if you can make composite materials either 3 times lighter or make them 3 times stronger, then you could substantially reduce this fuel cost. And by the way, this image you see on the right, this is an image that was released by NASA as a part of our institute. So this was the official announcement that they have some really good artist apparently that does all this. So this was so, if you look on the website, this was at least somewhat dedicated to our institute when they came up with this. Now, before I elaborate on that some more and what our institute does to solve that problem, I'm also going to give a little bit of background on something called the Materials Genome Initiative. Right? You remember there was when we're talking about the human genome, probably 10, 15 years ago, there's a lot of effort into completing the human genome. And about that time, people realized that we tackled that pretty well with a worldwide global effort. And so then the thought was, what happens if we devote the same type of global effort into solving a lot of our material problems, right? Because having material problems affects everything. You see that in the outer ring of the circle here: human welfare, clean energy, next-gen workforce, national security. What happens if we bring the world together to share our tools, our computational tools, our experimental tools, and all of our massive databases of material properties, and we populate these databases, we share them with the world? That's the Materials Genome Initiative, with the idea that if you have all this information and tools available to you, we can accelerate the development of materials for things like I've been talking about, manned missions to Mars. All right, so that's the Materials Genome Initiative. This came out in Barack Obama's administration. This was a White House initiative, and so if you go look online, that was the beginning of it right there. Now, this brings us to our second poll question, which I'll ask right now. So, what term is used by NASA and the Department of Defense to classify the maturity of technology? So option A is the Technology Maturity Index, MTI, or is option B the Technology Validation Number, TVN? Is it option C, Maturity of Technology Level, MTL? Or is it D, Technology Readiness Level, TRL?
Well, the obvious one would be to guess C there, but are you a tricky professor?
Well, I have some students online here. I noticed. You could ask them for sure. But as the votes are coming in, you can see there's clearly a couple favorites for sure.
Well, D looks like the favorite, Technology Readiness Level.
Yeah, so as we approach 125 votes, which is where we maxed out last time, looks like we have a total of 168 people online, but looks like we're kind of leveling off here at 127. So there's clearly some people who know their stuff out there, right? Yes, the answer is D, Technology Readiness Level. If you've ever done research for Department of Defense or NASA or maybe some other agencies as well, like NIST or places like that, you know that TRL is a very, very well-known metric. All right, so let me explain this a little bit. Technical readiness level. Here, let me advance my slide. So D is the right answer. Yes, and you see right here, I copied and pasted this off the internet. This is the TRL chart. So technical readiness level starts all the way at the bottom. All the way at the bottom is where most of us professors are, the majority of us professors. That is basic technology research. That means we're doing the very beginning of this research. We're trying to publish a really cool paper on it just to show that it's feasible and it can be done. That's TRL level 1. And it slowly creeps up. Some of us folks at the university do a little bit more applied research. That gets up to the TRL 4 or TRL 5 level. So that's what basically that's sort of the upper edge of university research. Then when the technology is mature enough to go to a company to develop further and possibly commercialize it and put into production, or as you see at the top there, in NASA's terms, actually have it on a launch system, right? System test and launch, kind of like some of our satellites that the Aerospace Enterprise puts up. That brings it all the way up to TRL level 9, right? So we go from TRL level 1 to TRL level 9. Now, in the history of materials research, typically research coming out of a university, it is always around TRL level 1. We make this amazing material that we could take a little piece of it, hold it in our hand and show the world, look what I made, isn't this cool? But it's really hard to take that and put it and make a rocket out of it, right? So keep that in mind here as we go to the next slide. So given the fact that manned deep space travel is extremely expensive, given the fact that NASA has figured out if we can make materials much lighter or alternatively much stronger, right? And given the fact that this is not going to do us much good unless we can really scale it up and make it so that a company can make these materials. And given the fact that this is a really hard thing to accomplish without the help of many people around the world, we get to these set of requirements that NASA put out in the solicitation back in 2016. So what NASA specifically said, they put out this solicitation for space technology research institutes, which I'll get back to that in a moment. They said that they want a group to come up with the next generation of composite materials with one, a 3-fold increase in tensile properties. So for you engineers out there that understand the concepts of tensile strength and tensile modulus, they wanted a material, a composite material, which has a specific tensile strength of 3 GPa per gram per cc. You know that GPa is for those of you who take mechanics of materials, you know that GPa is a metric that we measure modulus and strength by gigapascals. But in terms of an aerospace material, sometimes it's nice to normalize that by the mass, which is the grams per cc. So 3 GPa per gram per cc is a pretty daunting number to get to, right? As far as strength goes. As far as modulus goes, 150 gigapascals per gram per cc, again, is a pretty imposing number to achieve. Which because most really stiff and strong materials are also very heavy materials, like steel, for example, right? But they wanted a material that could break the mold and get to these very high levels of stiffness and strength. They also wanted, you see the next sub-bullet point there, a 50% increase in fracture toughness. So fracture toughness is resistance to crack growth. So if you have a crack in the material, you don't want it to grow. Right. And so obviously you don't want it to grow because you don't want your structural integrity to be compromised in the spacecraft. So they want interlaminar fracture toughness of 0.3 newtons per millimeter. So for those of you composites people who understand fracture toughness, or mechanics people, for a composite material, that's a pretty difficult number to achieve. The next major bullet item you see there, they wanted panel level testing, which is TRL level 4. In other words, they're not going to be happy with us if we make one little thing I can hold in my hand and do some very small scale experiments. They want something I can make a big, 12-inch by 12-inch panel of, machine some tensile specimens out of and actually test it like we normally would any sort of engineering alloy or traditional composite material. And also, they also wanted to make sure that we're not just doing this for our own sake, but we're doing it for the sake of everybody. So they wanted an MGI-based approach. That is, they want everything we do ultimately to make itself available to databases, the techniques we develop to be things that become ASTM standards and tools that are available to everyone, and computational tools that are available to everyone. And so they've asked us to embrace that approach. All right, so what we did, we put in a proposal, a group of us, and this was the first of this type of solicitation for Space Technology Research Institute. It was the first generation. There were 2 that were awarded. One was us, one was another one in a completely different area. But ours is the one that won with the requirements I showed you on the previous slide. So we won the award. It was, we named ourselves USComp, that is the Ultra Strong Composites by Computational Design. They wanted, one of the things they wanted to be computationally driven. And so that's what we're able to provide. Because our team has got Superior, a high performance computing cluster over in the Great Lakes Research Center. That was one of the key tools in order to enable this, us to get this award. So this is $15 million over 5 years. We started all the way back in June 15th, 2017. So if you're doing your math, you'll realize that we are in the 5th year of that. And I'll show you later on, I'll show you, well, in not too long from now, I'll show you where we are on that chart. Here's a picture of us. Actually, the last time we were able to get together before the pandemic, this was in October of 2019. Some of you may recognize this location. This is the beach on the Fitz. We all had a dinner at the Fitz. It was a very magical night. You could see perfect sunset. A group of people who have never been to the Keweenaw got to experience skipping rocks into Lake Superior. It was a lot of fun. As Bill Predebon said, we have 11 universities. We're the lead. We've got 2 material manufacturers. We have Air Force Research Laboratory, as well as 3 aerospace companies, Boeing, Lockheed Martin, and now Northrop Grumman, that are involved. Okay, let's go to the next slide here. So quickly, the list of universities here. We're at the lead. We have Florida State, University of Utah, MIT is a subcontract, Florida A&M, Georgia Tech, Johns Hopkins, University of Minnesota, Penn State, University of Colorado, and VCU. And we have NASA Langley Research Center, obviously involved, Air Force Research Lab, Nanocomp, which is also part of a Huntsman company, which is a bigger company. Nanocomp, by the way, is, we believe, the Western Hemisphere's largest manufacturer of carbon nanotube materials, which I'll describe here shortly. Solvay, Boeing, Lockheed Martin, and Northrop Grumman. Now, this brings us to the third poll question. This is a true or false question. Question is, carbon-carbon bonds are the strongest chemical bonds known to mankind, right? Remember, you always hear these things about diamond is the strongest material, right? Or you hear about carbon nanotubes. Question is, does this come from the carbon-carbon bonds? So we'll wait a minute. So it's either true or false, this statement. Probably the chemists are the ones that know the answer to this the best. I don't know how many chemists we have in the audience.
This is an interesting one. The strongest. I mean, the covalent bond is certainly a very strong bond. Is it the strongest though? Gosh, I'm not sure. If my life depended on it, I think I would guess false. But I just don't know.
Well, Janet, it appears that most people would
Yes,
agree
true.
with your gut instinct there, that the answer is false. So it looks like we're kind of, we're at most 53% false, 47% true. Really, the answer is definitely false. The carbon-carbon bond is not really the strongest. A lot of people think that. In fact, I used to think that as well. But then you're researching it, you realize it's not the strongest. But here's the thing. There are stronger bonds. But carbon-based bonds, carbon-carbon bonds really are magical in a way. In the engineering world and material science, they are really magical because you can build things out of carbon-carbon bonds. You could build diamond if you want to. You could build carbon nanotubes, graphite, all kinds of carbon-based materials can be made, because carbon, it's like Legos, right? Or Tinker Toys. You could assemble carbons in all these different ways that most elements you can't assemble them like that, right? I mean, you could do that to a certain extent with things like silicon or whatever, but carbon is really magical. So it can form all these allotropes. It can form polymers. You can have a polymer backbone chain. And also carbon is very lightweight. It's at the very top of the periodic table. So it's lightweight, which of course in the world of aerospace is really what we're looking for. Okay. So let's go on here. So what? So think about everything we need. We need really strong composites. We need them to be lightweight, right? Many of you are familiar with these things called carbon nanotubes. So carbon nanotubes, as you might guess, is the heart of us reaching these goals that I showed you a few slides ago. So this is a chart. The reason why I put this up is because this is what NASA published based upon our institute when it was first awarded. And you can see MGI, it's materials genome. The concept is we take all of our computational simulation tools, like you see it at the top, you see carbon nanotubes right there. They're actually collapsed and folded, but nevertheless, those little dots you can see, even with the low resolution, are individual carbon atoms. We can model these materials at the molecular level, and we could do it at the atomic level. We could do it all the way up at the structural level. At the same time, we're developing carbon nanotube-based materials on the experimental side, which you see in the lower left right there. You see in this TM image. So these carbon nanotubes, we could do all kinds of things with them. What these are showing is that they're flattened tubes that are stacked on top of each other. Nanotubes, as you may know, are extremely strong, extremely stiff. They definitely rival diamond in a lot of ways, and they have other properties that are useful as well. And if you can stack them up like this, it's a novel way to actually basically pack them in so you can take more advantage of their strength and stiffness. So we develop these computational tools, the experimental tools, and at the lower right, you see that we develop a database that people can access when they're designing aerospace vehicles or trying to design new generations of materials. They can access this data and take advantage of it. Now, this next slide, which we'll see here, I got to back up. What we see here is that this is the structure of Uscomp. And don't worry about the details of all the sub-projects. What I really want you to see is the big picture. You see the sort of the outer periphery. We have the TRL level 1 work, which is the materials design and exploration. So here's the group of people that we're playing around with models, materials, concepts. We're trying to understand a little bit about the materials and kind of form some really great ideas about it. Once we kind of develop those ideas, we go to sort of the middle part of this, the light blue part, which is the materials and manufacturing and characterization teams. And they actually attempt to take these ideas and make them, try to make prototypes of them and figure out clever ways to test them. And once we're confident we can make them, then we go to the lower right hand, we go to the material demonstration teams, which is now TRL level 4. And we actually make actual composite panels and we test them. And so this shows that we're trying to span the entire spectrum of TRL level 1 to TRL level 4 in our institute. And we've got individual teams that work together to do that. For some reason, my computer is a little bit slow to respond here. So where are we? So we're kind of getting to the end of the talk. And where I want to show is where we are right now. And we're very proud of this. So let's take a look at it. This is a complex graph that deserves some explanation. On the horizontal axis, you see specific strength. On the vertical axis, you see specific modulus. And if you take a look at this graph, if you look at the upper right, you see a little red diamond called project objective. That's the numbers I gave you at the beginning of this presentation that NASA wanted us to achieve. And if you look at all the way at the lower left of this graph, you see an orange dot labeled state-of-the-art quasi-isotropic composite materials. That's state-of-the-art. That's what's on a Boeing aircraft right there. You can see we got to stretch all the way from that orange dot all the way up to that red diamond in the upper right. And also you can see aluminum is there and that little blue dot in the lower left as well, just so you kind of understand. Now you see also the big red arrow pointing to the upper right. That's the direction we have to go with our technology. Now you see these little blue dots with sort of the red outline. This is the progress we've made during different quarters of our research. So in the very beginning, you know, we got up, the very first data point we had is quarter 6, right, which is in the second year of the Institute. You could see that by quarter 8, we made some new prototypes that were a little bit better. Then we kind of stalled for a while. We were kind of hitting some roadblocks, going up with the quarter 15 and 16, scratching our heads. Finally, we decided to change directions a little bit. We tried something new. And just within the last month or so, when we're in quarter 18, you can see we popped up all the way to that little dot, sort of in the middle top. And that's a huge accomplishment. So consider this, you know, NASA gave us some very steep objectives. In fact, the NASA folks have even told me that they didn't actually expect us to achieve those because they're almost impossible to achieve. But we're very proud that we've now created a composite material. And now you see that orange, that sort of middle orange dot, it's labeled unidirectional IM7 8552. That is basically the best state-of-the-art composite. You know, if you even make something better than what Boeing puts in the aircraft, you kind of get something like that. We're at the point where we are now stiffer. We have a material that's stiffer than that and almost as strong as that. And now and what you see, that quarter 8 data point, that was just a prototype of a new design we have. Now we're in the process of perfecting that, and we're expecting that dot to slowly creep over to the right and up a little bit and approach that red dot before the year is over. So we're really, really excited about this new jump, this leap we have in the technology. Okay, so that's all I wanted to say, and I think now we can open this up to discussion and questions.
Excellent. So proud of that quarter 18. That is impressive. it must have been frustrating to kind of be circling around, for a little while there and then to break through. So to ask questions, use the Q&A feature, which if you bring your cursor onto your Zoom screen, scroll down to the bottom, you should be able to touch the Q&A, feature, and then you can just type your questions in. And you can see there's already questions in there. So Greg and Bill, go ahead and start reading off questions.
Okay.
You should both be able to see them.
Yep.
Bill, you look very young. That's what. That's one of the first questions are. People are shocked you look so young.
I don't think that had anything to do with Mars, but but maybe it is. So one question is, what is the fuel for the trip to Mars?
Oh, that's a fantastic question, actually. So that's actually when NASA did the calculation. I never asked them what they were assuming, if they were assuming a solid rocket fuel or they were like assuming like hydrazine or something. I actually don't know. I should ask the NASA folks what they were assuming when they came up with that cost metric. That's good. I'm glad that question was asked. I'm curious now.
The question is that cargo cost to Mars a one-way cost?
Yeah, I forgot to mention that. That is a two-way cost. So NASA made that calculation for a trip there and a return trip back. But it's a very interesting question because there actually is a list somewhere. There's a list out there of that NASA keeps of people who are willing to go to Mars with the understanding that there's a very good chance that it could always be a one-way trip. And the waiting line for that type of trip is surprisingly long. There's a lot of people who would jump at the chance to do that.
There's an interesting comment here that you might want to comment on. It says, I think the only way the humans are getting off this rock is with every country participating, including China.
Well, yes, China, I was just seeing something online about they have mock-ups of some of our aircraft carriers, that you see in satellite images. Yes, if you look around the world, the technologies that we know of and don't know of, countries are racing to come up with a type of lightweight materials that actually enable things like this to happen. And unfortunately, a lot of those technologies are being developed for missiles as well. And it turns out that what succeeds in making lightweight missiles and fast missiles also succeeds with these rockets. So if we can kind of focus our attention away from missiles and more towards rockets, I think we could be more productive.
Janet, did you want to take over there?
Well, Jim has asked, what is the M&M building? And I'm trying to think of how I can describe that because I wasn't here before it was here. So how would I describe where the M&M building is relative to older alumni landmarks?
That's an interesting question. It's the one building that's on the side of the hill facing the water that's has a wide footprint. It's one of the farthest buildings to the east.
Yeah, Bill, maybe one way to describe it, it's right next to Douglas Houghton Hall. So it's just right next door to the west of Douglas Houghton Hall, for those of you who were here before the time of the minute.
And it's built into the steep bank down. It's built straight into it. So floors 1, 2, 3, 4, 5. On the one side, they've got no windows. On the other side, they've got this beautiful view of the waterway. And then there's a walkway that goes over the road to the other side of M&M. And so anyway, if you haven't been to campus in a while, that is one of our newer buildings. And I think it's been there for about 20 years, something like that.
Probably close to that.
Yeah. And it stands for Minerals and Materials. There you go. I answered your question, Jim. What is the fuel for the trip to Mars? Asks Harry.
Yeah, I answered that a few minutes ago. I don't actually know the answer to that, but I should find that out for sure.
There's a question about
Yeah, so the next question is China involved with this research? And the answer is absolutely not. I've actually been told very clearly that we cannot have any Chinese participation for the very reason I said earlier, is that this technology could be used to make hypersonic missiles as well. In fact, I even, that quantum leap that I showed in quarter 18, as soon as that happened, there's some materials out there we had to take off, take out of the media, and then because we made that quantum leap, we are that much step closer to having ITAR restrictions potentially put on this research. So, it's ironic, it's unfortunate, but it is ironic that, I talk about MGI-based approach. That is, we have to use the materials genome. We have to learn from each other. Countries have to learn from each other. But as soon as this project started, we realized right away that I had, as a group, we had restrictions placed on us by NASA, and the feds, the saying, look, you have some potentially very important technology, and for now we have to kind of keep it to ourselves. And so, yes, I am not allowed to work with China in any shape or form on this research.
Well, that you probably just answered this other question, which is that you can say, what did you change for the quarter 18 results?
Yeah, I can't talk about that. In fact, let's just leave it at that. I can't talk about that.
Okay.
Well, and there's some congratulations on the nice work and the progress from John, and thank you from Thomas. And then, can you comment on the effect of radiation on these materials and also temperature, because they would be out there at very, very cold temperatures and getting getting irradiated from the sun.
Yeah, exactly. That's a really good question. So, when we first wrote the proposal and got it awarded, the original proposal had us developing a material that not only met those mechanical targets, but had radiation resistance as well as temperature resistance to survive that. Then NASA came back to us after they said, we're going to get the project. They said, but we want you to make a change. We want you to not worry about the radiation resistance and the temperature resistance, only worry about the mechanical part, because according to them, if we can achieve the mechanical part, typically the radiation resistance and the temperature resistance is a little bit easier to add on top of that. Like they're talking about, okay, you could put coatings on it and things like that. We just want you to worry about the temperature or the mechanical property part. So yes, if this material were to be used, it would have to be somehow modified, maybe with a coating or something to achieve that. Now, with that said, though, some of the polymers we're looking at in this composite material are what we call space certified, which means they've already been tested in space, long-term tested. We'll like put it on the panels of the outside panels of the International Space Station for extended period of time. They do that routinely. And some of these materials have survived very well in that type of environment.
Well, and there's been quite a few questions added. If you kind of scroll down, there's some technical questions. Greg, do you want to pick one out?
Sure. Interesting. Can you comment on downstream challenges, which would be machining and bonding? Yeah, certainly. Those are problems. Actually, machining has been particularly difficult for us because if you think of it, if you're trying to make this material as stiff and strong as possible, machining is always going to be an issue. In fact, we have had problems with machining. Carbon fiber composites, you have these fibers aligned in a single direction. These fibers are what give it the strength and stiffness and toughness. Now, if you intensify that and make them even tougher, machining becomes an issue. So we have had issues with that. Bonding, we're not quite worried about bonding yet. That's one of those things we're kicking the can down the road a little bit because NASA didn't want us to worry about that. But eventually, we'd have to think about how to bond panels together. That's for sure.
Well, and I want to pick this question from Ronald. Did these new materials require new test methods and procedures?
Yes, they did. So for those of you who may be familiar with ASTM, which is the organization that develops standard test methods for all kinds of things, materials, paint, anything you can think of, that's where all the standards are. So there are many standards for composite materials. And we found right away that many of those were inadequate for this type of material. So one of our partners actually at the University of Utah, his whole scope on this project as a subcontract is to develop some specific test methods that are specifically developed for this material. And so that's what he's spent all his time on. He's been successful. So we have now new test methods that could be applied to this type of material, which is really nice for a materials genome initiative, because now we've got these new tests that others can use, because that's the type of thing we can share with the world.
There was a question by John Soring. It says, as new materials are developed, is there work being done to determine what to do with these materials at the end of life? He's involved with the process of investigating and investing in a startup company that has developed a way to process end-of-life materials to extract almost all of the carbon fibers in a near virgin state?
Yeah, that's a good question. There's a lot of work going on that. Really impressive. As of 10, 20 years ago, when you're talking about recycling thermoset-based composites, there was no answers. And now there's beginning to be a lot of answers on how to handle that. And there's multiple ways to do it. You could take composites that have reached the end of their life cycle. You can chop them up. You can create new materials with them. You can carbonize them and create, high temperature materials for specific applications. There are a lot of things you can do now in the world of thermosets. You can definitely have recyclable thermosets, which was out of the question in the past. I guess part of what he's getting at is what are we doing on that end? So what we're doing is we're trying to find the polymers, the thermoset, high performance thermoset polymers that will actually make this work. With the idea, if we can find one that actually makes this work, then we can go the second step and start looking at recyclability. How do we find a material if we can raise the temperatures to a certain amount? They vitrify, as some people may know. When you vitrify, you change the form of it so it's recyclable, or just make it just outright, reformable. So that work is generally going on, but that is somewhat outside of the scope of our institute. But the materials we're developing could eventually, fall into that category of research for sure.
Well, and let's take this question from Darwin. And thanks, Darwin, again. While strength and stiffness are critical for space applications, has there been some consideration of space radiation impacts on long-term material properties? Previously, the composite matrix was typically the weak link for space radiation. Well, and you sort of answered that a little bit, that NASA is going to, try to solve that problem later after we get some of the specific, get further out along the curve.
Yeah. And yes, that is true. And also to the second part to answer that question, that some of the materials we are working with are space certified. Some of the polymers, they have been tested for long duration exposure in orbits, where you get a lot of solar radiation, you get a lot of cosmic radiation, plus you get the constant exposure to vacuum cold conditions. So already we do know that our materials do have some resistance, but as Janet says, also later on, NASA would worry about whatever coatings or anything that it would take to extend the life further.
So there was a question, you answered part of it. It says, what loads is the material required to resist heat, cold? But the one that perhaps you haven't addressed yet is impact.
Yeah, impact. So impact resistance, that's very important, which is somewhat related to that toughness metric. So I gave an interlaminar fracture toughness metric, right. But one of the ways to measure interlaminar fracture toughness is impact. And of course, we know out in space, impact is a problem because we have all kinds of space junk in orbit. And even if we get out of our orbit where there's no more space junk, we've got all kinds of other things. There's all kinds of rocks and stuff. So the question is, are we going to make a rocket that can survive those impacts? And that's actually part of the reason why there's that fracture toughness metric, is to make sure that we could resist impact for sure.
So the next question is kind of about future students. So for somebody thinking about kind of wanting to be involved in this kind of area about developing advanced materials, what do you suggest they study for their undergraduate degree? And then
I love that question. I love this question. So it's funny how this works out. I have if you look at my graduate students, they come from all kinds of different disciplines, right? I have a course, I've got mechanical engineering students. Will, who I think I saw was on here, he was a chemical engineering student. I don't know if Ivan is on. I've had material science students. But what's interesting is one of my students who graduated a few years ago actually was a mathematics major, right? And you would think, what does math have to do with developing composite materials? As it turns out, it has a lot to do with it. And Matt Redu is his name. He was, like I said, a math major. He brought all kinds of ideas that the rest of us didn't think about from his mathematics background. He did all this complex modeling. And so it just goes to show that even if you're, whether it's chemistry, physics, mathematics, sometimes even social sciences. We need help on the social sciences when it comes to any sort of space exploration. But in terms of materials development, any sort of engineering, anything with a STEM background, there is a place for that. And no matter what, if you have a STEM background and you're interested and you want to do this, you should pursue it because there's always a place for you.
There was a question, would this material be suitable for ballistics, that is tank warfare, for example?
Yeah, well, that's why I'm supposed to keep a lot of the information under wraps for that very reason.
Okay.
Absolutely. Yep.
Okay.
Well, that's right up your alley, Bill.
Right. Yeah. Hey, I like to blow things up. Yeah.
So who was in that team picture? Was that everybody from all the different universities and companies that came?
Yeah, that was that included several folks from NASA, from some of the companies. There's someone from the Air Force Research Lab in there. The vast majority of people there are faculty and staff and students from the universities. So yeah, it wasn't the complete group, everybody that could make it in that particular trip. I'd say that was probably maybe about 75% of the folks involved with the Institute were able to make it for that trip. Yeah.
There's so many questions still out there. So here's one. I'm curious too. I don't know much about nanotube manufacturing. Can you even vaguely describe typical nanotube manufacturing processes?
Yeah. So the stuff that's publicly available, there's different ways to make nanotubes. One way, if you think about it, one thing we have abundance of in this world is natural gas. We really do. There's a lot of natural gas. And so if you think about, if you could take natural gas, a lot of companies are looking into this, Huntsman being one of them. If you take an ExxonMobil, if you take natural gas and you pull off, it's CH4, if you pull off the hydrogen, right, you can make hydrogen gas, which of course for energy purposes, we love hydrogen gas. It's awesome. And what you're left with is pure carbon. Well, that's what a carbon nanotube is, pure carbon. So one way people are looking into it is making it out of natural gas. Nanocomp, the company we work with, what's publicly known is that they make their carbon nanotubes. They have a proprietary, for lack of a better term, cocktail, an organic cocktail that they put into a furnace. They spray it into a furnace, a high temperature furnace. And under those high temperatures, the hydrogens and the oxygens and the nitrogens get driven off and you're left with pure carbon. And you pull that pure carbon material out of the furnace and you have a carbon nanotube material. There's groups like our MIT colleagues who are in the Institute, they make nanotubes their own way. They'll grow them in what's called a forest. So they'll put a little catalyst down inside a chemical vapor deposition chamber. So they'll put a little like an iron catalyst or nickel catalyst. They'll let carbon atoms float into the gas and they'll settle on them. And carbon atoms like to assemble like little building blocks like Tinker Toys. So they'll naturally form carbon nanotube forests. So that's another way to make them. But there's plenty of other ways that people are looking into it.
Excuse me, there was a question on, are you using 3D printing in your studies?
Yeah, so one of the things actually, NASA was interested in this early on because at the time this was awarded, our colleagues at NASA Langley were looking into 3D printing, putting nanotubes inside the feedstock for 3D printing. So yeah, that's of an interest to NASA. They did not want us to focus on that because 3D printing, the one downside, the Achilles heel to 3D printing is that we still haven't developed a way to make it void-free, completely void-free. And in order to achieve triple strength, triple modulus, we're fighting right now. That's our main battle right now, is to get rid of voids in the material. So that's why for this particular material right now, additive manufacturing is really not the focus.
All right, so this is now from Jeff. For modeling the composites, are you able to use commercial codes or are new codes required to design and model the composites?
Yeah, I like that question. So there's a multi-part answer for that. So we're doing modeling from the atomistic level, which is computational quantum mechanics. DFT, densital functioning theory, is what we, and my colleague Ravi Pandey over in physics and his graduate student Geeta, they're the ones doing the work on that. So we start at that level, and then we go to the molecular dynamics level where we're modeling actual molecules. And some of my students are online here, do that kind of work. Both of those are commercial codes, right? We use a commercial code available for both those levels. But then we go to the next length scale up. And the next length scale up is kind of like a no man's land of modeling. It's called the mesoscale. And there's really no good commercial codes for that. So our colleagues in the Institute at University of Minnesota, he does mesoscale modeling which is not down at the molecular level, not on the microscopic level, but in between. And he develops his own codes for that. But then once you get to the microscopic level, then my colleague down in Virginia Commonwealth University, he uses commercial code for that. So yes, so commercial codes are useful for some of this, but some of it, there's no commercial codes available.
There's still so many questions. We've answered 26 though. We have 16 open. Do you see any you want to answer?
Yeah, so there's one I'll address. Actually, one of our alum, Pruthel, he did his master's degree here several years ago, and he went on to get his PhD later on at Alabama. So I'm happy he joined us tonight. He's asking, how does the compression strength of the composite stand as compared to IM7? So what he's asking, IM7 is the standard carbon fiber composite. IM7 is known to have a weakness in compression. Carbon fibers, when you can actually compress them, they're weaker than when you pull them in tension. And so what he's asking, do our materials exhibit the same type of weakness in compression? Yes and no. As far as we know, they appear to be slightly weaker in compression, but not to the magnitude of IM7. That's probably the best answer I have for that right now.
Where is Pruthel working now?
I don't know, Pruthel, where are you working?
You're going to have to ask another question to answer it, Pruthel.
Yeah, that's right. He was a graduate student postdoc at the University of Alabama. And I'm sure he told me where he is since then. I have a hard time remembering all that.
So what happens? What happens when this stuff goes up into space where there is no atmosphere? What happens to the material's strength?
Yeah, actually, that's a good question, and that builds off of Bill Kortenbrock's question. So Bill Kortenbrock is asking, how does atmospheric pressure or lack of it impact the strength of the material? It's interesting. It's an interesting question. As it turns out, though, atmospheric pressure, when you're talking about the type of loads that make a material fail, when you're actually doing like looking at pure material, not structural properties, but material properties, atmospheric pressure is very low. But where atmospheric pressure does come into play, if you think about building a habitat on Mars, right, or the moon, and there's a person inside, people need air pressure. Again, they're selfish, they need pressurized air. So what happens now, if you have a pressurized vessel where a human is living in an atmosphere where there's either zero atmosphere like on the moon or a very small atmosphere like on Mars, yes, the material is subjected to pretty high loads. And yes, we have to make sure these materials can withstand those type of tensile loads. That's for sure.
There's a question on what will happen with your team at the end of the 5-year research cycle.
Another good question. That is something that I get asked on a daily basis these days as we're getting close to the end. Well, we will probably get a no-cost
By me as well.
Yeah, we will probably have a year 6 of a no-cost extension because of COVID and the pandemic, it was difficult to spend money for about a year. So we will have a no-cost extension. So we'll have a year 6. We are looking at ways to even extend it further, maybe with more NASA funding, or maybe somehow this evolves into something else where we develop the materials even further. So that's definitely something we're trying to answer.
It's very impressive work, Greg, and the amount of coordination that must be needed in order to kind of keep the communication lines open across all those, universities and manufacturers and government agencies. It must keep you up at night.
Yeah, it does. I have lost sleep over this for sure. Yeah. The hard part is when you have a large group, actually that brings up an interesting point. When you have a large group of companies, government organizations, university professors, and students, you have a lot of stakeholders, and all these stakeholders have different interests. They do. And so when you have a large institute like this, you have to balance all of these stakeholder interests. Graduate students want to publish papers. They really need to publish papers because they need to get jobs, and publishing papers is the best thing to put on their resume, right? So naturally they want to publish papers. Professors love publishing papers too, but professors want money, right? They want to squeeze more money out of me because they want more students. So that's natural. The government folks, they want us to be very careful about this because for them, publications are not as big of a deal. They want results, right? And sometimes having results and publications conflict with each other in a way, in some certain examples. So I am constantly on a daily basis trying to balance all that to try and make everybody happy, or as happy as I can make them.
Mm. All right, we heard back from Pruthil. He is at Baylor University now working as a research scientist, and he says, thanks for answering my question. And then a question from Darwin, another question. It seems as if accurate testing is critical for this program, the US Comp program. Unidirectional testing can be challenging in sample preparation, strain gauge orientation, and tab bonding. Have you developed any key test processes?
Yeah, that's funny. We were just having this conversation last week with tab bonding. So what that means is, when you're pulling, like if I use my phone as an example here, let's say my phone is a tensile test specimen. If you're going to pull this and test it, you got to grip it, right? You got to find a way to grip it. Now, he's right. Typically, if we're testing the fiber strength, the fibers are going up like this. So if you're gripping and pulling it, you're pulling along the strongest part of it. Now, if you think about pulling this hard enough, if it's strong enough, your fingers will not be able to grip it enough, and your fingers will start slipping. So typically what we do is we put tabs on it. That is, we put things on there, kind of like, if you're working in the kitchen, you use oven mitts sometimes. If you're trying to open a jar and you can't do it with your hand, sometimes you'll get a towel or oven mitt and you'll try and grip it a little bit better to open that jar, right? It's the same thing. You put an interface, more of a high friction interface to tab it, to pull it. But these materials along the fiber, they are so strong, even when we tab it, we're having a hard time breaking these specimens. And that is an active concern that we have, trying to figure that out. And my colleague at the University of Utah, I think, in my opinion, he's the best there is at this type of thing. And he thinks he has a solution to it. I think he's going to tell us about it next week. So it's a very timely question, and I really appreciate it.
It is an excellent question. All right, so here's a comment for Bill from Darren Hervey. It is good to see you again, Dr. Predebon. The last time I saw you was in the days of Dale F. Stein for when I was your student in thermodynamics and other meme courses. Congratulations on your 46 years of support to Michigan Tech, improving the education courses and experience to many students. And then example, aerospace course activities, which resulted in MTU's next student built satellites. Wow. So leading off the season in January, and I'll show you the lineup once I have it done, but we will be hearing from Oris. So that I believe is around January 22nd. So we're talking about next season already, Greg. So we are coming close to the hour. I always like to kind of give our guests a chance to kind of give a few closing remarks. Let me begin by thanking everybody for coming again. You have been with Michigan Tech's Husky Bites, sponsored by the College of Engineering. And we have been joined by Dr. William Predebon, who has been the chair of Mechanical Engineering, Engineering Mechanics for 25 years. And this is his last year, unfortunately, of being chair. He's going to be retiring. And then we've also been with Greg Odegaard, who is also a professor in MEME, which is the Department of Mechanical Engineering, Engineering Mechanics. So with that, I'm going to turn it over to Greg to say a few remarks, and Bill, you get to close us out.
Yeah, so I have one interesting thing I want to say. I want to thank everybody. I mean, this is a fantastic turnout. 120 people on Zoom. I know there's others on Facebook. That is fantastic. I'm really honored to have this much interest. The other thing I'm really honored by is having Bill be the host. So I don't usually tell this story, but it's amazing. The things that Bill has accomplished. When I first applied to this job back in 2002 or 2003, probably 2002 actually. I applied. I knew nothing about Michigan Tech. At the time I was a postdoc at NASA. I was applying everywhere. I had multiple interviews. I got a call. I applied for the position here. I got a call, and someone on the search committee said, Greg, why don't you, we see on this resume you go to the ASME conference on a regular basis. Bill Predebon, he's going to be there in a month at this ASME conference. Before you interview here, why don't you just go meet him and talk to him? And I thought, okay, I'll do that. So here I was, a postdoc. I didn't know anything. Nobody knew me. And I go to meet Bill Predebon. I know nothing about Bill. And I meet him at this conference. He was hosting a reception like he used to do every year. And I spent 5 minutes with him. And I thought, you know what? I would love to work with that guy. I really would. And actually, that is probably the major motivation that I accepted the job here. And I have been so lucky for 17 years to work with him. I mean, he's been so supportive, a phenomenal department chair. He's supported me from day one. A lot of this wouldn't be possible without him, quite frankly. So it's an honor for me. You know, Janet, you had suggested he be the co-host, and I immediately said, yes, that's a brilliant idea. So thank you, Bill, for everything. I really appreciate it. You're going to be missed terribly when you retire.
Thank you.
Well, he's just going to be down the road. So, you know, he's not disappearing. All right, Bill, give us the last few remarks and thank you both again for joining us. Bill.
Well, I want to thank all the people online and the people asking questions. They were very good questions for all of us. And I'm very proud of Greg, what he's accomplished. And I also want to thank Janet for initiating this Husky Bites. It's been fantastic with the number of people that have joined it over this past couple of years. And particularly the people that ask the questions. And it's very nice to have that. It's a pleasure to be a part of this, Janet, and to those of you out in the audience. And again, Greg is a very special person. We're really proud of him.
We sure are. All right, with that, go Huskies, and we'll see you next week.
All right, thank you. Bye.